Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is a second one focusing on oblique impacts, this time starting with both spheres on the move. We've already looked at the general background to this. We started by looking at a direct impact where there's a line of centres and nothing else to contribute to the dimensions of the problem, but now we're moving to a situation where the impact is oblique, and that means that at least one sphere is moving at an angle to the line of centres. We made several assumptions. The first was that the spheres are uniform and smooth. The second is that the spheres have the same radius, and the third is that they move without rotation. So we've now got A and B both moving and approaching each other like that. Again, that will set up a line of centres. The moment of contact gives the centres defining the line of centres. So there we are, and we use that to define our axes, the x-axis along the line of centres and the y-axis at right angles to that. Our velocities afterwards will be perfectly general, but we'll find once again that there are principles which allow us to calculate what the new velocities are in terms of the old ones. So again, we'll use a system of a diagram in the upper half of the slide, which is the situation before, and a diagram below, which is the situation afterwards. So we'll show a perfectly general set of velocities in two dimensions, uv for A and wx for B. And after that, we'll get our principles used to work out what happens in the lower diagram. What are those principles? Well, firstly, that impulses change in momentum. Now that has the consequence that since we assume the spheres are smooth, there's no force acting in the y direction that's perpendicular to the line of centres, and that means to say there can be no impulsive interaction between the two spheres in that direction. So conservation of momentum in this case means that each sphere's separate component of velocity will be conserved. The v and the x, to just put it succinctly, will be carried over to the position afterwards. The v and the x will be unchanged. So there's no change in momentum for either of them, and that's the consequence. There'll also be conservation of momentum for the component along the line of centres, but that's more complicated. So that summarises the situation so far. Let's now move into action on a particular problem, and note that the thing that makes it a bit easier is that when we put in the velocities for afterwards, the v and the x, the v and the x are unchanged. So let's take a particular problem now. Two uniform spheres A and B, masses m and 2m kilograms. A is moving with force meters per second at an angle of 60 degrees, and B at 1 meters per second, also at an angle of 60 degrees, but according to the diagram. So B has got a component along the line of centres towards the left, whereas A's is to the right. And we're asked, using the coefficient of restitution as 0.25, to find the speeds of A and B immediately afterwards. Now, finding speeds is in a sense not what we want to know, because the problem has to be formulated in terms of velocity components. So that's what we've got to do first, and only when we've got the answer to that problem can we move to finding the speeds. So we'll begin with the vector form of the approach velocity for A. It's 4 cos 60 because we resolve the 4 along the line of centres and get 4 cos 60, and for the B it's going to be very similar, but it's not 4, it's 1, and we have to remember the sign, the minus sign, to show that the inclination of B is leftwards rather than rightwards. So we can use the usual values for cos 60 a half and sin 60 root 3 over 2 to get a simplified version of the incident velocity for A, and similarly for the incident velocity of B. Righto, that's our diagram set up for the incident situation, the before situation. There we are. And afterwards we've got the important principle which makes things much simpler, that the 2 root 3 and the root 3 over 2 will carry forward unchanged. So when we put on the e as 0.25 and we set up the two velocities afterwards, after the collision, we'll have those two values carried forward. So it boils down to finding u and v. Well, for u and v, we've already used momentum perpendicular to the line of centres. That's why we said the components were unchanged. Parallel to the line of centres from momentum, we'll have m times 2 plus 2m times minus a half. That's the momentum beforehand. And afterwards, from the bottom diagram, that will be m times u plus 2m times v. Let's simplify that. We can lose the m's and get 2 minus 1 is equal to u plus 2v, and so a final simplification is that 1 is equal to u plus 2v. That's using momentum components conserved along the line of centres. We've also got the law of restitution, which can be applied along the line of centres. So looking at the components, the approach velocity will be 2 plus a half, strictly 2 minus a half, and that's got to be multiplied by 0.25, the coefficient of restitution, in order to get the velocity of separation, which in component terms, which is v minus u. Notice in my diagram I've inclined both the red arrows afterwards to the right to be consistent with u and v being positive. Then if they turn out to be negative, I'll know what that means in the diagram's terms. Now let's simplify. We need to multiply by 8, I think, to sort this out. So 2.5 times 8 is going to give us quite a big number. 2.5 times, but it's 2.5 times 8 times a quarter, so it's 2.5 times just 2, that's 5, is equal to 8v minus 8u. So that's our second equation carried forward, and those two equations we'll have on the next slide. So 1 equals u plus 2v and 5 equals 8v minus 8u. So there we are, a somewhat neater version of the calculations, but we end up, I'm glad to say, with the same equations. Now those equations we need to solve simultaneously, so we carry those two forwards just like that as the starting point for our algebra to work out what u and v are. So if I multiply the first equation by 8, then I'll get 8 is equal to 8u plus 16v, and then if I add the equation that begins with 5 to the one I've just written in, I'll get 13 is equal to 24v. So that allows me to say in one more step that v is 13 over 24. That could be a bit messy now, but in fact the first equation is so simple that it will make it easy to get u. So if we use the first equation, the one beginning with a 1, we get 1 is equal to u plus, and it will be 13 over 12, which makes it easy to see that u is going to be minus a 12th. Right, now the only two unknowns on the diagrams on the left are the u and the v, which I've just found. So we can look at the lower diagram, the after diagram, now knowing what u and v are. So let's do that on the next page. There we are, we've got our calculations, that just summarizes the answer. So now let's do that on the next page. The two components, the minus 1/12 which we worked out and the 13 over 24, are now in place on the diagram. So we can work out the speeds as requested using a Pythagoras calculation. So the speed of A will be equal to the square root of, and it will be 1/12 squared plus 13 over 24, plus 2 over 2 root 3 squared. Well, 1 over 12 squared is the square root of, is 1 over 144. And the square of 2 root 3 will be 4 times 3, that's 12. Well, I won't push that calculation any further as it's now a matter only of numbers. I'll look at the second speed. So the speed of B is equal to 13 over 24 squared this time, so that will be 169 over 576, but I'll write it as 13 over 24 squared for the moment, plus, and root 3 over 2 squared will give us 3 over 4. So a bit of number crunching to do now, but basically we've got the answer there. So we'll carry that forward to the next page, where I got as far as the answer I'm underlining, and the same for the other expression. Those are the two things we were working out, and I've used the calculator to crunch the numbers to get the answers 3.873 etc. and 3.465. Again, I remind you I'm using the convention of using dots when I get too lazy to write down any more, but that's basically what the calculator display shows, and then I'll correct that to give an answer in context. So there we are. The speed of A is 3.87 meters per second, and the speed of B is 3.47 meters per second. Well, that brings us to the end of this video, which is the next to the last in this series, and the next one looks at the loss of kinetic energy in calculations of this sort, and at the angles of deflection that you get in an oblique collision.